Say sorry to her.
Me? Who?
Shannon. Thank you.
Shannon and Akanksha and anybody else watching this, I apologize. I almost forgot. Felicia over there didn't remind me to record. Lauren over here didn't remind me either, Akanksha. So I had to remember on my own, which is feeble.
Oh, wow.
We're just talking about Chapter 12, Chemical Kinetics, the rate of reaction. So you'll have to just take a look at this and read it on your own. I'm moving on. When we describe how fast a reaction goes, there's something that we write called the rate law. In science, a law is a relationship. I'm not talking about law, like the Constitution, that you need to follow it or you get punished. In science, the law is a relationship. So the rate law is an expression, a mathematical expression that we use that describes how fast a reaction is. No. The rate law is going to be something new. There's two different forms of rate law.
Do they mean the same thing?
They do mean the same thing, but they're going to look very different. Yeah. It depends on what information you're given. If you're given the concentration versus the rate, then we're going to find something called the differential rate law. And if you're given the concentration versus time, we can find the integrated rate law. Differential, integrated. What does that sound like? Yes. Yep, differential and integrated. Some of us had a calc test today. Now, just as you asked, these two rate laws are going to look very different from one another. You'll see them both today. But they do wind up giving the same information. They tell us the same. Both of them tell us how fast the reaction goes. But they're going to look different from each other. These last two bullet points are real important. You need to know that you don't find the rate law just by looking at the chemical equation. We have to actually run the experiment and measure something to be able to find what the rate law is. Yeah, we're going to spend like a couple of days finding the order of the reactants. Well, yeah, I need to get into that a little bit. The midterm is questions taken from AP exams over the years. So you can study for it by studying all the AP exams from like 1970 and on. Or I'm going to give you a study packet. That's where we get the questions on the study packet from. And then the midterm itself is going to be questions off that study packet.
Same with the final?
No, the final is going to be cold. You're going to get it cold.
Why?
You will not have seen the questions on the final.
Isn't it tough? The final's tough. Don't people do that?
I got all of them right.
That's great. That's great.
Aiming for a B, you can get 100. All is well.
Yeah, it seems like the final was kind of tough.
A lot of people's grades get like dropped from a B to an A.
No, no.
We'll
We'll review quizzes. We'll prepare for the final. Yeah.
So
Yeah, those questions will be the same. The numbers, though, will be changed. They won't be the exact. I don't want you to memorize the answers.
How many questions are there?
Around 40 or 45, something like
The
that.
study guide is also 40 or 45.
No, the study guide has, I think, 150 questions. Yeah, yeah. You'll have plenty of time. In fact, before Christmas, I'll give it to you, so there'll be plenty of time. And so that you can leave it there until like the week before. Just
Have you noticed for like the start class, is the the final worse for us? Like, do we do worse on it? It's like the last final.
No.
Oh shit.
No, I don't know how much that matters.
It's like,
Well,
it was like final speed and it's like.
wouldn't it be the
Yeah,
second final?
I know a lot of times, yeah, the 6th hour you do the worst out of all your exams because you're just tired. Thank you, Divya. Was the top off of that?
Yeah.
Thank you for that. Okay, so now this thing, the order. You read that and you write it down and you're like, okay, what is the order? The order of the reactants. Here's what order is. You know what, let me go on to the next slide and then I'll show you what order is. I'm going to put a shade up so we can only talk about part of this at once. So I know this title is integrated rate law, but this would be the form of a differential rate law. I'm going to show you both in this one slide so you can contrast the way they look. The differential rate law has this form, so I'm going to give you a moment and I'll let you write that down. Then we're going to talk about all the parts of that.
Is that an
Is the n power yet?
That's just moles.
No, no. It represents the order. N is going to be the order in this case.
Okay.
K is the rate constant. Yeah, I'll go through all
N?
those.
Equilibrium constant? Rate constant?
Wait, is that
It's no, it's a
moles?
lowercase k. So yeah, we use the same letter, but a different.
Just like
Yeah,
five reading.
yeah, yeah. I know. So this is what a differential rate law looks like. It always says rate equals, and then these terms. K represents the rate constant. The rate constant really is what tells us how fast the reaction is. The higher the K value, the faster the reaction goes. You know, we can talk about slow reactions like iron rusting. That's slow. Or we can talk about fast reactions like a bomb exploding. That's really, really fast. Every single reaction has its own K value. Things will affect K, like the temperature. If you increase the temperature, the K will go up. It'll make the reaction faster. If you take a gas phase reaction and you pressurize it, usually that makes the reaction faster because the particles are able to collide with each other more frequently and cause reaction. So there's several terms that go into what makes a reaction faster, and all kind of is built into K. Then we have reactant. Remember, those brackets represent the molarity. So we're talking about the concentration of the reactants raised to a power. That power is the order of the reactant. Now, the order of the reactant, as it mentioned on the previous page, the order tells us how much the concentration affects the rate. So what I'm saying is, if you increase the concentration of the reactants, the rate's going to go up. So the more reactants you have in the system, the more frequently they're colliding, and the faster the rate goes. Now, when we have that exponent, the exponent we call the order, and that's going to tell us how much the concentration influences the rate. In other words, if n is 1, if it's a first order reactant, that means that if we doubled the concentration of the reactant, the rate would double, because it's just being raised to the first power. That's the most common order, is first order. Again, if I double this, then the rate doubles. If I triple this, then the rate triples, that kind of thing. If I cut this in half, the rate gets cut in half. So first order is very simple. Whatever change I apply to the reactant concentration, the same change happens to the rate. Albany?
Could you quickly repeat the definition of order?
Yeah, it tells how the reactant concentration influences the rate. If it's a second order, it's possible to have a second order reactant. That means that if I double the concentration of the reactant, then what happens to the rate is the rate goes up by 4 times. Because if I double this, then it's 2 squared influence on the rate. Colby.
Like what if, okay, so your reactants, like what if it's like 3 and 2? So the coefficients of that. So like
No, the coefficients in the reaction don't dictate the exponent. It's not like equilibrium constant.
Okay.
No. And that's why I said you can only determine what the order of everything is and what the rate law is going to be by doing an experiment and running the reaction. You can't look at the chemical equation and find anything about the rate law. Samir?
Wait, so is the reactants the concentration of the reactant? So when we're finding the moles, like moles over liter, is the liters of like, what if it's like not solution?
Yeah, no, this is only going to be for solutions or for gases. Because we can measure the molarity of gases, how many moles of a gas are in a liter. So yeah, it's going to either be gases or aqueous things. Yeah. Solids and liquids are not going to play a role in this. Yes?
So there's certain orders of the signs of reaction. So like, wouldn't, if you like already know, for example, like the order of like formation of an H2O, is it the same every single time?
Yes, yeah. For that reaction, it's always the same.
Okay, so like if you have it like memorized for some reason, like you don't have to.
Yes, that's true. Yeah, yeah. I don't see how you would memorize any or why you would use your brain on that, but yes, you're good. Okay, so that's, remember, we find the differential rate law when we know concentration versus rate data. So we change the concentration, we see what happens to the rate. If we only know the concentration versus time, that's when we use the integrated rate law. And we're going to find it by actually doing an integral. But that's the part I'm going to spare you of. So now, check this out. If we have this reaction is just an example I'm going to do. I like it because it only has one reactant. So we can only have one thing to focus on. The rate of a reaction is always going to be dictated by how much reactant we have. If you have a real high concentration reactant, it's going to go fast. So during the reaction normally will slow down because we're depleting our reactant amounts, and so they'll collide less frequently over time. So usually the reaction is fastest at the beginning.
So if there's multiple reactants, you just find a limiting gradient and solve that.
No, you'd have to find the order of each of the reactants. It doesn't matter. In this chapter, it doesn't matter which one is limiting, which one is excess. Yeah.
So you would like solve the rate for each and then add them together?
Yes, that's what you'll do. Yeah, you'll solve for the order and add them together. Yep. Now, what I'm telling you, we don't have any evidence of this. You just have to trust me that this reaction is a first order. So there's the first thing you can memorize. Whenever you see this one, you know it's first order. And it is first order. But when we look at this thing, I know that there's a 2 coefficient. That does not mean that this is second order, though. So we have to undo that equilibrium constant, K, and not just take the coefficient and raise it up to the power. The order is only found by running the reaction and figuring out what the orders are. And we're going to actually do that. Our first lab that we do, that bleach food coloring lab is described up there, we're going to be monitoring the concentration versus time of one of the reactants, and we're going to see what the order is. Okay, now I'm going to go ahead to the next slide, and that's where we're going to, don't write this down because that was what was on the last part of the previous slide. There's the chemical equation. It's a first order reaction. Now first order means this. First order means this. The definition of rate is the change in the reactant concentration over time. The rate law for a first order reaction is K times the one reactant concentration raised to its order, which is first order. So both those are expressions for what the rate is. That means that they're equal to each other.
So how is this different from the differential?
Oh, I'm going to show you. This is where, if we evaluated this change, the change in the reactant concentration over time, over a time interval, this is where the calculus is going to come in. Notice my deltas, the only thing that's different here is my deltas became d's. It's a differential equation now. You can put the N2O5 term over on the left with the dN2O5, move the I always want to call T temperature because I'm a chemistry brain, not a physics brain. Put the time term over there and integrate both sides. Regan, get to it. And anybody else that loves calculus, do it. Move the N2O5 over here, move the dt over to the right side, Now what we have is the integral of 1 over N2O5. What's the integral of 1 over x?
X to the negative 1 power?
No. That's what you're starting with. What's the integral of x to the negative 1?
Bro, I'm in pre-calc now.
Oh, you're in pre-calc. I'll give you a pass on that one. So anyway, yeah. If you haven't had Calc BC yet, you don't know that. I'm just rattling that off for the people who have had Calc BC. Here's what we would find. Now again, I'm not showing you this because it wouldn't mean anything to most of you. This is what you would get. This is what we would call the integrated rate law for that first order reaction. So the differential rate law, remember, I'll just put diff, is rate equals K times N2O5's concentration to the first power. We can also describe the rate of the reaction using this. The concentration of N2O5 changes with time according to this equation. ln of N2O5 equals negative KT plus ln of N2O5, 0. Now this term at the end, N2O5, 0, that's the initial concentration. So whatever concentration the reaction started with for the reactant, maybe it started at 1 molar. So that's what it was at the beginning. The 0 down there just represents the initial value. And we'll use that all the time in here. So anytime you see a concentration with a little 0 subscript, that means that's what the initial concentration was in the reaction. This is at any point in the reaction, during the reaction, at time t.
Okay, so that's the final formula?
So this is what the integrated rate law looks like. So as I tell you, that looks a lot different from that. But really, they both have a K in them. That matters. Remember what K tells us. K is the rate constant. Tells us how fast the reaction is. Now, the K is a constant. This term at the end is a constant. So really, we only have 2 changing variables in this expression. The ln of N2O5 and the time. And since we have 2 changing variables, and K is a constant, what kind of relationship is this?
Linear.
Variable, constant. It's a linear relationship. Yes. So that means this. Look at this. If we were to plot the natural log of N2O5, the reactant, over time, it would give us a straight line. What's the slope?
It's going to be KT.
Yeah, it's going to be negative K. The slope would be negative K. K is always a positive number. So, and the graph of it would look like that. That's our graph of the natural log versus time. Natural log of the reactant concentration versus time. It goes down over time. The natural log goes down. The natural log goes down in a linear fashion. I put K. I should have really put negative K because it's a negative slope. K's got to be positive. So you take the opposite value of the slope, and that's what the K value is. K represents the slope of that line. So the steeper the slope, the faster the reaction goes. The steeper the slope, the faster the reaction. That's why I say K is really what tells us how fast the reaction is. Wow. Now the walls are going to start moving together. Pretty soon they'll be screaming. The term at the end here, that would be the y-intercept. So here's what I'm telling you. This part that's written in red, I'm going to have a red part for all 3 of the next, well, this and the next 2 slides. Write that down in your book and highlight it. I'll highlight it too. Because I like it when this does this. When you plot the natural log of the reactant concentration versus time, if you get a straight line, that means the reaction was first order. The reactant was first order. Now the only common orders are first order, second order, and then back to zero order. So zero, first, and second are really all we'll ever do. Yes?
So you said it's the order of the product, so is it the same as the order of the reactant? Or sorry.
No, we only talk about the order of the reactants. Because it's the reactants that are actually reacting, causing what the rate of the reaction is. Stay with me, Sachin.
Okay, Sachin, speak up.
Now, for the second order example, I'm just going to give you a fictitious generic A yields B. And we find by running an experiment that A is second order. What would the integrated rate law look like for this? I'm going to go through it a little bit faster this time because, again, we don't need to know how we got to it. But just like we did before, the rate is, in this second order example, this is the differential rate law right here. That's the differential. I'll put DIFF. That's what it always looks like is rate equals K times the concentration of whatever power. That power is the order of it. So yeah, we find that it's a second order, so it's now got a second power. So again, what that means is if we double the concentration of A, the rate will quadruple because it's being raised to the second power. If we triple A, the rate goes up by 9, 3 squared, right?
Wait.
Yeah.
What if you
Okay, I'm waiting.
if you think about it like when you square it, right? It would be 2 squared, which is 4. But like that just doubled. Like the
That's just in that one case.
You understand?
Yeah, but then triple it. The rate's going to go up by 3 squared, which is 9.
2 squared is 4.
And 2 times
But
2
it
is 4.
starts at 2, right? The A value begins at 2, and then it becomes 4. So isn't that just like 1 again?
Yeah, in that case. Right, in that case it would be double. Wait a minute, time out. If we started with 2 for A, okay, so start with 2 for A. The rate would be 2 squared, which is 4.
Yeah.
Now, go to 4.
Oh, that's true.
Now, the rate would be 4 squared, which is 16, which is 4 times more than what it was the first time. So the rate would quadruple. Yep. Yep. Okay, so anyway, that's equal. Remember, this is how rate is defined, is the change in A over the change in time. So that means this. I'm just going to cut right to what the actual integrated rate law is without deriving it at all, or even talking about it. 1 over the concentration of A equals the KT. Now, notice this is positive KT. In the first order, it was negative KT. But this is positive KT plus 1 over A0. And so the same thing happens. If we have K being a constant and whatever the initial concentration was a constant, then we have the graph of the line. It's ugly, but it works. It's true. So if you have a second order, when you plot the inverse of the concentration of the reactant versus time, you'll get a straight line.
So then how will you be able to tell?
You have to do the graph. One of them will give you a straight
How will
line.
you be able to tell if it's first order or second order?
Because if it's second order, then when you graph the concentration, the inverse of the concentration of the reactant versus time, it's going to give you a straight line. If it's not second order, it won't give you a straight line, it'll be curved. You'll either get a straight line for the second order graph or the first order graph, or the zero order graph, which I haven't shown you yet. But one of them will be straight, and the other two will be curved. It'll make sense when I do an example, but I'm not going to do an example until Monday, when you tried to forget all of it.
Are you complaining?
Just be like that, bro.
I'll tell you about the reading quiz in a moment.
It's a group thing.
Okay, now check this out. One last type of order. If you have the same chemical equation, A yields B, but A is a zero order reactant. Zero order means that the concentration of A does not affect the rate. It means you can have a real high concentration or a low concentration, the rate's going to be the same no matter what. As long as you have A there, then it's not going to affect the rate. What's that?
The more iron you have, it doesn't affect the rate.
That's right. Yeah. Yeah. So solids and liquids will always be zero order. Yep. Because their concentrations really are not changing. Yep. Yeah, write this down. This one is big. So there's our three orders. This one, if it's zero order, it's just concentration of A equals negative KT plus concentration of A0. Simple. Yeah.
So first order includes natural law. The second order, the order is like 1 over the reactants.
The inverse, yeah.
And then.
And third order is just the straight up concentration. Did I say third order? Zero order.
Thank
Is
you.
the straight up concentration.
Zero.
This is zero order. We have zero first and second. I just did them in a bad order. Like when they named the laws of thermodynamics. You need me to go back?
Yeah.
That's the wrong direction.
I'm still.
I know, you don't expect to understand it. You won't.
Okay, thank you.
You're hopeless. No, that's not what I'm saying. No, what I'm saying is this. We really need to see an example. This is what an example. Now, don't write anything down. I want you to just put your pencil down and look. We'll start with this. I'll do a little recap on Monday. But we're going to take this. This is just copied right out of the book. Whoops. My question for you is going to be, okay, how do we find what order the reactant is? We have concentration versus rate, not versus rate, concentration versus time data, and we want to know what the order of the reaction is. There's only one reactant. It's H2O2 is the reactant in this, is the decomposition of H2O2. So what we're going to have to do, and this is a lot of fun, we're going to have to make 3 graphs of this data. One graphing the H2O2 concentration versus time, one graphing the ln of the H2 concentration versus time, one graphing the inverse of the H2O2 concentration versus time. One of those 3 is going to be a straight line. The one that's a straight line is going to tell us what the order is.
So
There's no other way to, I guess there's another way to do this, but that's the simplest thing to do. What's that?
So if you don't want to do that, you just do the experiment?
Right. But the experiment's already been done, so now we just have to analyze it.
Oh.
Right? It's already been done. So the graphing calculator is going to be, let me have your attention. The graphing calculator, use your graphing calculator if you know how to graph with it on the homework. You still can't use one on the test. However, because you can't use one, I'm not going to have you graph 3 graphs on the test by hand. So I would either give you the graphs or I would describe the graphs. So I'll give you enough that you could answer the question without having to make the graphs when you do the test. However, when you're doing the homework problems, I do want you to do the graphs. At least do one of the problems doing the graphs so you know how to do it and what to do. Okay? I have already graphed this with the 3 graphs, and I'll show you what they look like. And it's not bad. I mean, this turns out to be very simple. But I know that right now you're kind of fuzzy. It won't always be. Okay, that's it. We're done. Yay.